Okay, so I would like to prove this little result here. I'll call it a proposition. It says if phi from A to B is a star homomorphism, then phi of A is closed. So the image of any star homomorphism is closed. To prove this directly, we need a lemma. And maybe a nice way of saying this is that suppose B in phi of A SA is given, then there exists A in A SA with phi of A is B, and the norm of A is the norm of B. Right, so suppose I have an element which I already know is in the image of phi and it's self-adjoint. Then of course I can write it as phi of A for something in A. Right? But the lemma says that I can choose this A to be self-adjoint and to have the same norm as the element that I already had, the one that I called B. So the proof of the lemma goes like this. So take A prime in A, so that phi of A prime is B. Note that phi of the real part of A prime, which is phi of the average of A prime and A prime star, is the average of phi of A prime plus phi of A prime star, and that is the average of B plus B star, but B is self-adjoint by assumption, so it's just the average of B and B, so this is B. So without loss of generality, A prime is self-adjoint. So we may as well assume that the A prime that I chose the first time around was self-adjoint. Now consider the following function. So here I have minus the norm of B, and here I have plus the norm of V, and the function that I'm then thinking of goes like this, and then continues like this, and like this. This is my function f. Note that f applied to B is just B, since f is the same as the identity function on the spectrum of B, because the spectrum of B, we consider this a red set, and the spectrum of B lies somewhere here. Right. Now the A that I have chosen, I don't know so much about its norm. Sorry, the A prime that I've chosen, I don't know so much about its norm, but we can set A to be f of A prime. So very likely the norm of A prime is bigger than the norm of B. So we have spectral values that are outside the interval from minus B to B, but that doesn't really matter for our purposes. So since the range of f is contained in the interval from minus b to b, we see that the norm of A is the same as the norm of B, and then of course f of A prime. So since phi of A is phi of f of A prime is f of phi of A prime is f of B is B, the lemma is proved. So this takes care of our lemma, and now I'm ready for the proof of the proposition. So what is it I want to prove? I want to prove that the image of phi is closed. So I will fix some b lying in the image of phi's closure, and a sequence an coming from A, so that phi of an converges to B. So note that, of course, B, I can always write this as the real part of B plus I times the imaginary part of B. And so if I could prove that the real part of B and the imaginary part of B lie in B, then, lie in the image, then I'm done. So note it suffices to prove that the real part of B and the imaginary part of B in fact come from the image itself and not the closure, and that since phi of the real part of an converges to the real part of B, and phi of the imaginary part of an converges to the imaginary part of B, just because of the continuity of the star, we may assume that real B and im B are in the closure of the self-adjoint elements of SA. Right? So, I mean, my assumption is that B lies in the closure, so that means that I can approximate it by something called phi of an. But if I work with the real part of B, I can see that this is approximated by phi of the real part of an, and that is self-adjoint. Right, so in fact what this means, so I'll write it as a without loss of generality, hence an and B are self-adjoint. I do this, of course, in preparation of using the lemma. Now, the next thing we can then do is that we can say, let's let yn be phi of an plus 1 minus phi of an. And then we note the sum from n equals 1 to n of yn is the sum for n equals 1 up to n of phi of an plus 1 minus phi of an. And this is a telescoping sum. So I get the first term out, a big N plus 1, and I get the last term, well, the last term and the first term, right? So all the other terms, the ones that have indices between 2 and n, they will simply cancel out pairwise. So this converges, of course, to to the element that I call B minus phi of A1. So this sum here, the infinite sum, makes sense and it converges, and the sum is B minus phi A1. So of course it would be possible to replace the first element A1 with 0, and then I would have to subtract this element. But in a second I want to do a without loss of generality argument, and then I would sort of get an A1 back. So that's why I'm keeping this. So I really would like for my my series here to be absolutely convergent. And this is not the case. I mean, this is not, I don't really have any control of this, but I'm claiming that we can arrange this. So what is it that I would like to say here? So by passing to a subsequence, if necessary, without loss of generality, we may assume that the norm of phi of an plus 1 minus phi of an is less than something. It doesn't really matter what it is as long as it's summable, so I choose 2 to the minus n. Right, so how can I arrange this? So I know that phi of an goes to b, so this is a convergent sequence, and then using, then it's also Cauchy, and then I can just sort of choose in the subsequence so that the elements are so close to each other that the difference is less than 2 to the minus n. Right, and this, of course, is what I called yn, right? So yn's norm is less than 2 to the minus n. So we see that this sum here, yn, is finite. So in fact, the sum 1 equals 1 to infinity of yn is absolutely convergent. Now, what is it that I know about yn? So note that yn lies in the image of A, self-adjoint. So by lemma, I may choose xn in A, also self-adjoint. So that yn is phi of xn, and yn's norm is the same as the norm of xn. We get that this sum here, 1 to infinity of the norm of xn, is finite, because it's the same as the other one we just looked at. So this sum here is absolutely convergent, hence convergent. So we can say that the sum n equals 1 to infinity of xn is x. So here I used my lemma, right? So the lemma sort of tells me that since I have an absolutely convergent sequence in B, I can lift it to an absolutely convergent sequence in A. And then now I just need to note what is phi of x. Well, it's phi of this sum, and by continuity of phi I can pull this inside. Phi of xn, and this is yn, and we know the sum of the yns, it is b minus phi of a1. Right, so what is b? b is phi of x plus phi of a1, that's phi of x plus a1, and it lies in the image. And this is what we wanted to prove.